So the register organization of 8086 consists of many different types of registers. The first section is called general purpose register. Second one is the pointer or the index register. Third one is the segment register, then instruction pointer and the status flag. Now, purpose of the utility of the general purpose register is to store the information, and all these registers which are used in 8086 are of 16-bit. They are 16-bit registers, and every register has its own functionality. Since they belong to a certain category, so they are categorized in the form of a general purpose register, pointer or the index register, segment register, instruction pointer, and the flag register. The purpose of general purpose register is to store the information. If we want to store 16-bit information, we will be calling it as AX, BX, CX, and DX. If it is used to store 8-bit information, then AH, AL, BH, BL, CH, CL, and DH, DL. So only 4 16-bit registers are used for as a general purpose register. The functionality of accumulator is very much similar to the functionality of accumulator in 8085. Pointer and the index register are used to point the memory, and as previously told, that address used in 8086 is represented by 20-bit. If I say 20-bit, it means 5 hexadecimal digits will be used to locate the individual memory registers. So since we don't have any 20-bit register, but even though we use 20-bit address, and for generating the 20-bit address, we will be using 2 registers, 2 16-bit registers. And what used to happen, one is called the base address. This 20-bit address is composed of base address and the offset address. And the combination of base address and the offset address is going to give us the physical address of the memory. So pointer or the index register points, it represents the offset address of this 20-bit. And segment registers are those registers which are known as base address, which used to provide the base address. Now, why we call it as a segment register and why we call it as a pointer register. Now, normally in 8086, whatever memory is being used, we have already seen if we are using 20-bit address line, so 2 to the power 20, yani it means we can fetch, microprocessor can fetch 1 megabyte of the memory, because 2 to the power 20 is equal to 1 megabyte. 1 megabyte in comparison to 8085, which used to fetch only 64 kilobyte. So it means the accessing of the memory, the capability of accessing the memory is more in case of 8086 processor. So what we used to do, the memory is managed in the form of a segmentation. Every memory of 1 megabyte is divided into 16 sections of, and each section is of 64 kilobyte. So 16 sections, and each section is of 64 kilobyte. Total capacity of the memory will become 1 megabyte. So individual sections are known as segment. That is why we use the concept of memory segmentation. Instead of using the 1 megabyte of the memory as whole, what we do, we divide this memory into the sections. And individual section used to store different kinds of information. And these sections are known as code segment. These segments are called code segment, stack segment, data segment, and the extra segment. The meaning and the purpose of these segments is to put the coding, the instructions in a certain segment that is called as code segment. we use a certain segment of the memory as a stack segment, which will be working as a stack, which will be putting the data in a certain another section, another segment that is defined by the data segment. And similarly, extra segment is also used to store the information related with the data, especially it is used for the string operations. And the next instruction, next category of register is the instruction pointer, which is very much similar to the program counter, which gives the information in the form of the next instruction to be fetched. So basically, it is the combination of segment register and the pointer register, which is going to generate the 20-bit address. Now, the content of the segment register is of 16-bit. The content of the pointer register is also 16-bit. The content of segment register is known as base register, and the content of pointer or the index register is known as offset address. So what is being done? You have seen in the functional block diagram, there is a summer, address summer, which is used in 8086. And the purpose is to shift the content of segment register left 4-bit and then add the content of the pointer register into that, so that you will be able to get the 20-bit address. And that 20-bit address is being sent from the bus interface unit to the memory, either for fetching purpose or for writing purpose. And of course, the status flag is having same functionality as in case of 8085. The status flag is going to reflect any kind of arithmetic in the data logic operation which is being performed in the accumulator, and the result will be stored in the accumulator. So it is going to reflect the result after doing any arithmetic in the logic operation. Now, status flag is again of 16-bit in comparison to 8085, which is of 8-bit. In that 8-bit flag register of 8085, we use only 5 flags. Those 5 flags are 0 flag, sign flag, parity flag, carry flag, and auxiliary carry flag. In case of status flag of 8086, we use 16-bit register to store the flags. And out of that 16-bit, only 9 bits are used, means 9 different flags are used. Out of that 9 different flags, 5 flags remain as it is, as which we use in 8085. That is sign, parity, 0, carry, and auxiliary carry. And besides that, we have some more, 4 more flags: direction flag and overflow flag. We have carry flag, parity flag, auxiliary carry flag, 0 flag, and the sign flag as the same as of 8085. But besides that, we have 4 more flags: single step trap, interrupt enable, string direction, and overflow. So these 4 flags are more used in 8086. So this is the description of general purpose register. We use 4 registers which are used for storing the general information, general data, or the address in the general purpose register. Or if we want to store 8-bit, so we divide it into 2 parts, because individual register is made up of 2 8-bit registers. AX is the accumulator and others are the general purpose register. Besides the general purpose, they can also be used for the special purpose, as the BX register serves as a base register for the computation of the memory address. Means besides storing the data, BX can also be used to store the address, and it will be working as a base register for that in case of computation of the memory address. For a certain reasons, for a certain purpose, for a certain application, CX is also used as a counter. CX register is also used as a counter in case of multi-iteration instructions. Whenever we use multi-iteration instruction, CX can be used as a counter. And then DX is also used for the memory address when the data is transferred between the input output port and the memory using certain input output instructions. because in 8086 we have separate input output instructions which are used for either reading purpose or for the writing purpose. So DX can also be used, besides it can be used to store the data, 16-bit data, it can also be used to store the memory address. So this is the description of general purpose register. Now let us go and see what is the use of segment registers. Now we have under the category of segment register, we have four segment register. One is code segment register, CS, data segment register, DS, stack segment register, SS, and extra segment register, ES. So what we normally do, as I told you, that in 8086 microprocessor based system, the memory is divided into the four segments. The one segment is called code segment, data segment, stack segment, as well as the extra segment. Now, the code segment of the memory is going to hold the instruction codes of the program. The data, variables, and the constant which is given in the program are used to be held in the data segment of the memory. And stack segment is going to hold the address and the data of the subroutine. It also holds the content of the registers or the memory location given in the push instruction. And before attending any kind of interrupt, the microprocessor is going to save the content of the program counter on the stack. So also when the call instruction is executed, before the execution of the subroutine, the address of the next instruction is the address of the next instruction of the program is saved on the stack, very much similar as in the case of 8085. And as far as the extra segment is concerned, extra segment is going to hold the destination address of some of the data of a certain string instruction. We have the facility to manipulate the strings in 8086, and for that we used to use the extra segment register. Now the extra segment register, this holds the destination address of some of the data for while using the string instructions. Now, as far as the segment registers are concerned, the segment register points to the starting address of the memory segment currently being used. If we say that CS is representing 2000, it means the code segment register will be starting from 20000. So normally the segment register represents the address which is the starting address of that particular segment, which is divided in different segments of the in which the memory has been bifurcated. Now, as I told you that memory is bifurcated to store different kinds of codes. We used to store the code in a separate segment. We used to store the data in a separate segment. We used to use a certain segment as a stack. We used to use certain segment as an extra. And the starting address of the individual segment is being represented by CS in case of code segment, DS in case of data segment, SS in case of stack segment, and ES in case of extra segment. Now, segmentation, by doing the segmentation of the memory, we have many advantages. And that is why we do the segmentation of the memory. As yesterday, in the previous one, I have already told you that 8086 can work in a multi-programming fashion. If it is working in a multi-programming fashion, it means it is dealing with many console units, many users at a time. And the processor is going to allot certain time to the individual users. And for example, for first 15 seconds, it will be dealing with the first user. For the next 15 seconds, it will be dealing with the second user, and so on. So segmentation also helps in processing the information of the individual users. Because if there are 4 users, individual user will have its own code segment in which they will be writing their codes. The extra segment will be using the other user will be using different data segment, and individual users code segment, data segment, stack segment, and the extra segment is different from the other user. So processor has no difficulty in processing the information of the individual. That is the main advantage of doing the segmentation of the memory. Because it may be possible that if we don't do segmentation, then the codes of the individual user with which the processor is dealing, it might happen that both different user will be using same address for representing their code. But if we divide the individual memory, total memory, into different segment and allot the different segment for the different user, suppose we are using we have 4 code segments. We have divided the memory in such a way that we are using 4 code segment, different segments, and individual code segment is allotted to the individual user. So there is not a possibility. There is no possibility of getting clash in between the codes of the individual user. So as I told you that segment register is going to point the starting address of the memory segment currently which is being used. Now, if we take an example, then the code segment register is going to point the starting address of the code segment. Data segment register points the starting address of the data segment, and so on. And the maximum capacity of a particular segment may be up to 64 kilobyte. And that is why if we are using individual segments of 64 kilobyte, 1 megabyte memory can be divided into 64 kilobyte of the segments 16. So there will be maximum 16 segments, and each segment will have maximum 64 kilobyte capacity. Now, the starting address of the segment is divisible by 16, as this particular figure shows that the memory segment of 8086, this is the memory segment of 8086. Now, the segment which is shown in the figure are currently used segments, and there are more number of such segments to make the total memory capacity of 1 megabyte. So, as far as the 8086 is concerned, the 8086 instruction is going to specify the 16-bit memory address, but the actual address are of 20-bit. So this 20-bit address is being calculated using the content of the segment registers and the effective memory address, or you can say it as a offset address. So meaning thereby this 20-bit address which is generated in case of 8086, it is a combination of two 16-bit addresses. One is given by the segment register, whatever it may be code segment, data segment, or stack segment, or extra segment, depending upon which segment we want to use. And another 16-bit address is given by the effective memory address or the offset address, which is given by the pointer registers. Now, this effective memory address or the offset address, we have to compute in a variety of way, and the variety of way by which we used to define this effective address or the offset address is known as its addressing mode. So it depends upon the addressing modes in which the effective address will be signified. So that we will discuss later on, that what are the different addressing modes and how the effective address are being taken depending upon the addressing modes. Now, for the execution of the as far as the stack instructions such as push instruction, pop instruction, call instruction, return instruction are concerned, the content of the stack pointer and the content of the stack segment register are used to compute the address of the stack location. It is fixed. For fetching any location in the stack segment register will be providing the base address, and stack pointer will be defining the effective memory address or the offset address. And the different other index registers such as source index register or the destination index register, these all together along with the segment registers such as data segment and the extra segment are used to perform the string operation. So this is all about the segment registers. Now this is another figure of the segment register which represents that segment register are going to hold the upper 16-bit addresses of the 4 memory segments such as code segment, data segment, extra segment, and the stack segment. And this is known as the base address or the segment base. Now, once this 20-bit address is being generated, then bus interface unit is going to send this 20-bit address to the memory. And this bus interface unit, always it is going to insert 0 for the lowest 4-bit of the 20-bit address, and then it is being added with the effective address to get the physical address. Now here you can see that we have memory locations, and individual memory has been divided into different segments. This is stack segment of 64 kilobyte. This is stack segment of 64 kilobyte. This is code segment of 64 kilobyte. And if the code segment register contains 348A, it means the starting address of the code segment will be 348A0. And the top of the code segment register will be 4489F by adding FFFF into that, because FFF represents the 64 kilo. So in this way, this is the functionality of the segment register. Now let us discuss this instruction pointer. Now this instruction pointer in 8086 microprocessor, it is going to act as very much similar to the program counter in 8085. And the purpose of using the instruction pointer is to provide the address of the next instruction to be executed. Now, which is the next instruction to be executed? Suppose we are talking about code segment. The starting address of the code segment base is 348A. So the starting address of the code segment will be 3480. So the next address will be 348A1. The next address will be 348A2. Next address will be 348A3, then 4, then 5. And similarly, we are going to add so that we will be getting. So if it is executing 348A0, the next will be 348A1. It means this address, which will be generated just because of 348A1, will be generated along with this base. If we add 0000 in this, we will be getting 348A. So actually, CS is 348A. It is shifted 4-bit left, so that right hand side you will be getting a 0, and then you add 00001, so that you will be getting 348A1. So normally it is being done with the help of the instruction pointer, which is going to point the address of the next instruction to be executed. And how it is being done, as in the case of microprocessor 8085, whenever a particular memory location is being fetched, which is given, whose address is given by the program counter, when it is fetched and executed, automatically the program counter is going to be incremented by 1. In a very similar fashion, the content of the instruction pointer is going to be incremented by 1 for the further proceeding. So now see, the example is here. The start of the code segment is 348A, and how it is being done. What we used to do, whatever is the content of code segment, it is shifted 4-bit right, and so 0 is implied here. And then if I see that instruction pointer is 4214, then we add these two addresses to get the 20-bit address. So this address is called base address. This address is called effective address or the offset address, and this address is called the physical address. So every time whenever a memory has to be fetched, either for the reading purpose or for the writing purpose, it is required to generate the 20-bit address. And this generation of 20-bit address used to happen with the content of two 16-bit addresses. One is given by the segment base and another is given by the pointer register. So here you can see that if the instruction pointer contains 4214, so the effective address to the physical address will become 38A, B, and 4. And then once 384A, B4 has been fetched, the instruction pointer automatically increments itself by 1 so that it will become 4215. And the next instruction which will be fetched will be 38AB5, which is the next. So in this way, this 20-bit address is being generated. Now, the content of the instruction pointer, that is IP, and the content of the code segment register is normally used to compute the memory address of the instruction code to be fetched. Now, this we are talking about the instructions which are stored in the code segment. If we have to fetch the data, we have to take care of the data segment content as the base address and any one of the pointer register, source index, destination index, point, which will be giving the effective address. And very much similar in this fashion, that the whatever is the content of the base register, it is shifted 4-bit left, 0 is placed here, and then added with the content of the pointer register into that. In case of fetching the instruction, we are using instruction pointer. But in case of fetching the data, we will be using other register, not the instruction pointer, because instruction pointer only is a pointer which points only to the code segment. If we are working with the data segment, the data segment register will be giving the base address and effective address will be given by any other register besides the instruction pointer. So code segment register points to the base or the starting of the code segment, and the instruction pointer contains the distance or the offset from its base address to fetch the next instruction byte. Now, so it means whenever we have to calculate 20-bit address, it consists of two addresses. One is called base address and another is called distance address or offset address or effective address. And the combination of these two addresses are going to generate a 20-bit address, and that address is known as physical address. So this 20-bit physical address are represented in the form of a segment base colon offset rather than in a single form of CS oblique colon IP. For example, if I say code segment is having 348A and IP contains 4214, so it automatically means that this is shifted 4-bit left so that 0 is here and then 4214 is added into that so that we are able to get the 20-bit address. Now this is the flag register, and we have 9 active flags and rest of the bits remains unused. Bit number 1, bit number 3, bit number 5, bit number 12, 13, 14, and 15 are unused. The first bit is representing carry flag. Third one is representing parity flag. Next one is representing auxiliary carry flag, zero flag, and sign flag. And all these flags are having same functionality as in the case of 8085. If there is a generation of carry flag will be set. If the parity flag, if the even number of parity flag will set. If there is a BCD operation which is going to perform and sum is more than decimal 9, auxiliary carry flag is going to set. If the resultant is 0, zero flag is going to set. If the D7 bit means the most significant bit is going to become 1, the sign flag is going to set. So these flags have the same functionality, but we have 4 more flags which is used for the different purpose. The one is called trap flag, single step trap. Second one is called interrupt enable flag. direction flag, and the overflow flag. So these flags are used for the different purposes. And carry flag, parity flag, auxiliary carry flag, zero flag, and same and sign flag has the same functionality as that of the 8085.